In this video we're going to talk about residue systems, and residue systems have to do with modular arithmetic, and they are basically sets of integers which give you a complete remainder set. So to give you an intuitive idea of this, let's take mod 3. Then a residue system of mod 3 consists of, for example, 0, 1, and 2, because these are all the possible remainders you can get when you divide something by 3. For example, when you take the number 6 and divide by 3, you get a remainder of 0. When you take the number 7 divided by 3, you get the remainder of 1, and the number 8, you get a remainder of 2. So any number you take and you divide it by 3, you're going to get one of these remainders no matter what. So that is why this is a complete remainder residue system of mod 3. Now this is not unique, that's not the only one. For example, I can change these, and I can just take any 3 consecutive numbers. So I can take 16, 17, and 18, and I'm going to divide them by 3. So 16 divided by 3, let's say I'm going to write it in a different form. I'm going to say 16 divided by 3 equals, the normal way of writing it would be, I would say 5 plus 1 over 3. But what if I said 4 plus 4 over 3? That's valid, right? Because we get 12 over 3 plus 4 over 3. So that means I can choose 4 as one of my set elements of the set instead. Now if I take 17 over 3, excuse me, take 17 over 3, the normal way of writing that would be 5 plus 2 over 3. But what if I want to write 2 plus 11 over 3? And that works because this is 6 over 3. So I can choose 11 as my second one. Now if I take 18 over 3, the normal way of writing it would just be 6 plus 0 over 3. But what if I want to write instead, I just want to keep it as 18 over 3. So I'm allowed to do that. So I can keep this as 18. Now this seems like a very awkward residue system, but it turns out it works, because if we just reduce it, this is really the remainder of 1. This is really the remainder of 2, and this is really the remainder of 0, just in disguise. And usually the easiest residue system is the easiest one to use, that 0, 1, 2. But it turns out that this is just as fine, and there's infinite different ones. So now we can also talk about something called reduced residue systems, and that means that only contains the numbers that are smaller than m, but relatively prime to it. So if we say we have a system of mod m, then the reduced residue system has all integers less than m coprime to it. So let me give you an example. So let's choose a sufficiently big number, such as, let's choose the number 7. So the number 7, the basic residue system would be 0, 1, 2, 3, 4, 5, 6. So which of these are coprime to the number 7? So coprime means that the only common factor they share is 1. So 0 does not meet that condition because they do not share the common factor of 1. But every one of these other ones does. And 7 is prime, and every prime, if you write its basic residue system, then the reduced residue system will have m minus 1 elements. So let's choose something that's not prime and give you an example as the last example. So let's choose the number 8. So the basic residue system will be 0, 1, 2, 3, 4, 5, 6, 7. Now 0 we can get off right off the bat. 2 is not coprime because it has the factor of 2, so we have to get rid of that. 3 is fine. 4 we have to get rid of. 6 we have to get rid of. So this is the reduced, or a reduced residue system for the number 8. It's just 1, 3, 5, 7. And you might be thinking, why is this even important? It's going to be important in a few videos when we start talking about Euler's totient function, stuff like that.